Continuing in 11.1, we next have Taylor's theorem and the remainder in the Taylor's theorem. So we have a function f of x, and we've approximated by some polynomial of degree n, and so it should make sense that the remainder after n terms is going to be equal to the function minus the polynomial. That's the terms that will be left. And so what we use is, to find the remainder, we say, well, it's got to be the next term. So the next term would be the next derivative. So if we were on the nth derivative, we're now at the nth, n plus 1, over n plus 1 factorial, and then we are centered at a, and c is some number in the interval between x and a. And then after you develop that, it turns out that the actual remainder theorem, the estimate of the remainder theorem, says if I want to find the remainder after the nth term, it's going to be the absolute value of f of x minus the polynomial of degree n, whatever n we decided on, which has to be less than or equal to, and then we are going to come up with the maximum error that this piece right here could be. Actually, not the n plus 1. This up here. We're going to call it m. And then we have x minus a to the n plus 1 over n plus 1 factorial, because our goal is to look at that n plus 1 derivative and figure out what number in my interval will make it as large as possible, and that's the number we're going to stick in. So we look at example 5. Find a bound for the magnitude of the remainder term for the Taylor polynomial cosine of x, centered at 0, so it's a Maclaurin series, using that formula. Okay, so we are going to have to take the absolute value, and I'll put the whole thing in absolute value bars, over n plus 1 factorial, x to the n plus 1, and then we're going to say that's got to be less than or equal to, okay, what's the biggest it could be? Well, let's look at that derivative. We're talking about cosine. And if you think about the cosine curve, graphs like this, the highest and lowest points are 1 and negative 1. So I could safely say that this absolute value here will have to be less than or equal to the absolute value of x to the n plus 1 over n plus 1 factorial. Because the biggest it can possibly be is 1, so I'm going to replace the f to the n plus 1 of c with a 1. And so it wants to know, it says now if you want to approximate, they went a little further. If you want to approximate cosine of 0.1, using that, Taylor polynomial p sub 10, then when you do this, you would end up getting a remainder. Now, it doesn't have all the work here, but after the 10th term at 0.1, it'd be less than or equal to 0.1 to the 11th over 11 factorial, which is approximately 2.5 times 10 to the negative 19. Okay, number 6. Estimating the remainder for e to the x. Okay. Estimate the error in approximating e to the 0.45 using the Taylor polynomial n equals 6 for f of x equals e to the x centered at x equals 0. Okay, so the remainder formula is the n plus 1 derivative at c over n plus 1 to factorial x to the n plus 1. C is between 0 and x. Now, if you just keep on taking derivatives, no matter what derivative you take, it's always going to be e to the x. So if I take the n plus 1 derivative at c, it's going to be e to the x, which is e to the c. So r sub n is going to be e to the c over n plus 1 factorial x to the n plus 1. Now our boundary for c is between 0 and x, but x in this case is 0.45. So something between 0 and 0.45. And if you think about that, e to the c is an increasing function. And so we're going to have to say that e to the c, let's pick a place between. I'm not sure I like how the book set this up. But since it's an increasing function, the boundary here, 0.45, would be the biggest it could ever be. So e to the 0.45 is actually 1.56. So we could top it out at 2 and say, we safely could say that e to the 0.45 would be less than 4 to the 1/2, which is 2. So I could replace my e to the c with a 2 and say that r sub 6 of 0.45, not x. Let's start again. R sub 6 of 0.45 has to be less than 2 times 0.45 to the 7th over 7 factorial, which is approximately 1.5 times 10 to the negative 6. The thing is, you picture m to be bigger than the highest possible value. If you go through and you do the Taylor polynomial at p sub 6 of 0.45 in your summation, 0.45 to the k over k factorial, you end up getting approximately 1.5683114, and it does have an error that does not exceed 1.5 times 10 to the negative 6, because e to the 0.45, oops, I'm having a problem with that 4, is 1.568312185. So it's fairly accurate.